So we continue this morning session with Professor Gregory
Fiete.
Fiete. I want to say it all wrong. Fiete or something. From Northeastern University. Professor Fiete is a doctor, a PhD graduate from the physics department at Harvard. Has had many postdoc positions, Calvin, Caltech, and has had very nice awards for Science Fellow in Theoretical Physics, or perhaps currently is. And he won a, very nice Best Research Award by Alexander Stiftung. Very nice, yeah. So I'm very happy to that you're here. So the floor is yours.
Well, thank you so much for the invitation, Bernardo and Rafael. It's a great conference. It's nice to have this mix of physicists and mathematicians. It's actually the first time that I've had this sort of experience of being in a joint physicist-mathematicians conference. I had some affiliation with Station Q way back, so there was a little bit of an intersection at that time, but I was a postdoc then. Many years have passed, so it's nice to kind of, have that experience again. So I'm on the physics side of things, and the talk that I have here is meant to kind of be a survey of various projects that we're looking at in the group. It's okay if I don't get through all of it, but the basic idea is to look at basically light matter interaction and ask what can we learn about solid state condensed matter system from light matter interaction. In some cases, I'm going to consider the light to be very strong perturbation on the system. So the light is changing the properties of the system in interesting ways. So that's a way that we can control matter. But if light is weaker in its intensity, then we're probing the states. And of course, you can do both at the same time. You can have one laser pulse, which is very strong, drive the system in interesting phases, and then come in with a second light source and look at how it's absorbed or scattered to learn about the strongly driven system. So that's kind of in a nutshell where this talk is headed. And I'm going to try to focus on some more mathematical aspects for certain parts of the talk, the band topology, so that hopefully I can make a connection with the mathematical crowd. But even if that particular mathematical aspect is not of your interest, at least you can get a survey of the sort of experiments that physicists are doing. I'm a theorist, but I'll survey some experiments and think about how some of the mathematics of the quantum wave functions, particularly the many body states, might be able to be revealed in different types of experiments. That's a very vibrant frontier right now. So I'll talk about this quantum geometric tensor at one point, which is about wave function mathematical structure. And it's a very active area of research to try to understand what sort of measurements and what sort of physical phenomena reveal interesting information about that particular quantity. So the talk's going to be organized roughly in this way. So I'm going to talk about Floquet systems in the beginning, which is the situation where the Hamiltonian of the system is periodic in time. So this is an unusual situation until rather recently in the physics community. Generally, we like time-independent Hamiltonians because they lead to conservation of energy. That's the translational symmetry in time that gives rise to conservation of energy. If you have a time-dependent periodic Hamiltonian, you no longer have conservation of energy. It turns out that your energy is only defined modulo some frequency-dependent piece, integer multiples of the driving frequency. And so you no longer have a minimum energy or maximum energy in the system, and you suddenly lose one of your important cruxes in physics, which is, you find properties by minimizing energies or free energies. So in Floquet systems, that's gone. So it's a little uncomfortable from the physicist point of view to think about that. So we're also going to be interested in the way in which light is coupled to the matter. So I'll talk about what I call a direct regime, which is where the light is directly coupled to the electrons. So typically we're interested in the electronic degrees of freedom, and the lattice degrees of freedom, which are the phonons, usually play a supporting role to the electron. So in the BCS theory of superconductivity, there are phonons which mediate interactions between electrons and make them effectively, attractively interacting. So they like to clump together and form bosons, which then can undergo like a VEC and superfluid type transition, establish phase coherence for a superconducting state. So there they're kind of playing a supporting role. But in many cases, the phonons are of very direct interest. So I'll talk about something called nonlinear phononics, where the light is tuned to resonantly excite lattice vibrations to be large in amplitude, and then that changes the crystal structure in a transient way, and then influences the sort of electronic states that one can achieve in those systems. And I'll give a few examples to show what sort of phenomenology can appear. This will link with some earlier talks. I'm going to look at bilayer systems of these two materials, and we're going to change the interlayer spacing or a shear in these and show that you can modify the magnetic properties and even the band topology in this material right here through this nonlinear phononics regime. So that first bit is going to be looking at light coupled to the lattice in a high intensity scenario. Then I'm going to switch to light directly coupled to the electrons and give some motivation for how this reveals some aspects of the quantum geometry, the wave function properties of the system. I'll try to emphasize how, in many ways, this is very much in its infancy. Most of what is understood in the context of non-interacting electron systems. So there's a whole unexplored territory out there about quantum geometry for truly interacting many-body systems and what it reveals. So it's kind of, in a sense, an extension of all of the questions related to fractional quantum Hall effect and topological order, which we were just hearing about. And then, time permitting, I'll return to phonons and talk about something which are kind of new on the scene, which are called chiral phonons. So these are lattice excitations which break time reversal symmetry. In the simplest example, you could think of them kind of undergoing a circular motion in the material. So this means that they have like a finite angular momentum. So physicists in the field are very interested in angular momentum because, light which is circularly polarized carries angular momentum. Spin degrees of freedom carry angular momentum. And if we now bring in the lattice with angular momentum, then we now have interesting ways that we can couple light and magnetism and the lattice together through this introduction of chiral phonons. And I'll describe this material, cobalt titanate, which has a lot of interesting properties associated with it in addition to these chiral phonons. So, right. So chirality, there's a debate in the field about chiral phonons versus truly chiral phonons. So if you have a two-dimensional material, then they won't necessarily propagate. They can't propagate perpendicular to the plane, but they can move circularly in the plane. But of course, a chiral particle should propagate and then have motion which is in the plane perpendicular to its propagation. So if you have a 3D material, then you can have truly chiral phonons, but a 2D material is only going to support a simpler version, which is just kind of finite angular momentum. But in both cases, they have finite angular momentum. So that distinction is not going to be important for anything that I say, but for the experts, then it's good to know that. Yeah, other questions? Okay. So to motivate a little bit why it's interesting to look at how light interacts with materials, I want to highlight some of the different ways that light can be tuned and changed. So we can think about the polarization of light. So we can have linearly polarized light where the electric field of the light is just moving along a particular line. Electric field is just moving, say, within a plane. Versus circularly polarized light where it's rotating in time. If you were looking along the direction of the light, you would see the electric field rotating around versus just moving back and forth. And so, this circular versus linear polarization is very important in many applications, and the way that it couples to the electronic degrees of freedom is different in many cases, and it reveals different sorts of physics. So it's important to look both at linear responses from linearly polarized light as well as circularly polarized light. We can also change the frequency of the light, which gives us a tool to resonantly couple to different degrees of freedom, whether they're electrons or phonons, or they could even be magnons, so magnetic excitations. We can tune the frequency to target those specifically. We can change the intensity of the light, the number of photons per second that are incident on a material, and that's often an important parameter. Some systems display, for a given frequency of light, very different behaviors depending on the intensity of the light. So there's some interesting examples of achieving metastable states. So I could have some material that's in a particular phase, it has a particular type of magnetism in it, and with a single pulse of light of sufficiently large intensity, then the system can be kicked into a new magnetic state, which might persist for a very long time, like weeks or more. So it's metastable, but if it lasts for weeks, that's long enough for some sort of application. And so there, the intensity plays a very important role. You can change the angle of incidence of the light relative to the crystallographic directions. So you basically get different matrix elements and how the light is coupling either to the phonons, the magnons, or the electronic degrees of freedom, and that can reveal important information about the structure of the material. You can shape the pulse in time. So it's called chirping, but more generally you can shape it in different ways, because there's a pulse typically has a Gaussian envelope, and there's some frequency components within that Gaussian envelope, and you can change like the distribution, the intensities within those different frequencies. And this is used a lot in quantum chemistry to control reactions and reaction rates and that sort of thing. It's used less so in condensed matter physics, but the experimentalists tell me that they're very much interested in pursuing this direction. It's just another way that you have control. And then you can also use multiple drive lasers. So you can use one drive laser at one frequency, another at a different frequency, or you can have very different intensities of the two drives, and that leads to a response on top of a response. So you can get very interesting behaviors. So part of the outgrowth of my interest in this area comes from trying to understand what are the limits of control, like in an equilibrium static situation. So we can think about materials under pressure, strain, gating and that sort of thing, and see how a given material might be able to be pushed through a phase diagram as a function of different parameters. So if we relax the assumption of equilibrium and we're driving a system with light, then we just open up a lot more possibilities. So it's that's my motivation as a theorist, to explore possibilities of what we can do. Yeah.
This will be relevant for 2D materials or 3D materials. So the lasers don't penetrate that much.
It depends a lot on the, what is the electronic structure of the material.
So it's relevant.
Yeah. So, something which is transparent to our eye, we know that it has a gap in it which is bigger than visible light. So, like a window. So you can just look at a window and see, oh, I know that it has a gap in it, and that gap is bigger than visible light, because visible light goes right through it. But then it might absorb a lot in the X-ray or something else which is not visible. So whether a material is transparent or not depends very sensitively on the frequency of the light. Yeah.
How do these constraints enter into the time-dependent Brochet Hamiltonian? Is it through the electric vector potential?
Well, some of them, like pulse shaping and so on, it requires multiple frequencies. So it's not going to enter directly into flow K. So flow K is a particular limit, which I'll discuss in just a moment, which you can think of it as a very long pulse length in time. So if you're near the center of the pulse, then for this particular time window, you may see many oscillations of the electric field. It turns out you only need on the order of maybe 10 oscillations for the system to respond as if the oscillations are going on forever. So one of the things which physics is very forgiving in is like long time or long length, or large particle number limits are often achieved at very low particle numbers. So it's like, what is your liquid behavior in a 1D system, which is some kind of collective motion of spin and charge, which leads them to have different velocities. In order to exhibit that sort of behavior, you only need like 10-ish or 20-ish electrons to see this low energy emergent behavior. And so a famous example is the fractional quantum Hall effect also, which is many body effect, but Bob Laughlin did numerical calculations of 3 electrons to basically make an educated guess for the variational ansatz for the fractional quantum Hall effect. So he generalized from 3 to get one of the most important, like, many body interacting states. So if you know what you're looking for, and you can see the signatures, often, small particle number, short times, systems that are not that long still reveal the very interesting, like, thermodynamic limit sort of physics, which I think is great for physicists trying to understand this stuff. Things don't need to be perfect. Often they just kind of need to be in the right ballpark. Yeah. Other questions? Okay. So here's an example, flow K, which is to your question. So this was, one of the most beautifully visualized experimental manifestations of a time periodic Hamiltonian, but it's not time periodic. It's just a pulse from a laser which has oscillations in it. The number of oscillations, I think this is semi-realistic. It's of order 10-ish oscillations within this Gaussian pulse. And what is shown here is a time-resolved, angle-resolved photoemission spectroscopy. So this is a very important experimental technique. You send in a photon and you eject an electron. It's basically Einstein's photoelectric effect, which is one of the important early proofs that light existed in wave packets. So you eject this electron. The electron is then directed through a series of magnetic fields, and depending on how it bends, you can reconstruct its momentum and energy. And therefore, you can reconstruct the quantum state that it came from inside the material. So it's a way to measure the electronic band structure. And so topological insulators have these Dirac-like or linearly dispersing states on their surface, and they're ideal for seeing with this technique, ARPES, which is very surface sensitive because you're ejecting the surface electrons. So in this experiment, what Nuggetix's group did was drive the system with a pulse whose main frequency is below the gap in the material, so that you don't create any bulk resonant excitations, at least with a single photon, and you see primarily a surface response. And this is the Dirac cone you can project down in time. So at this point in time, there's no oscillating field. At this point in time, there's no oscillating field. But in the middle, when there are oscillations over this time window, so the system kind of looks periodic locally in time, then you see signatures of the flow K structure, which is basically you have band structure which looks the same, but these band structures are replicas of this Dirac linearly dispersing cone, but stacked on top of one another with the stacking distance, which is Planck's constant times the frequency of the light. Yeah.
So you don't close the gap. So is it correct that your Broca topological index is trivial in this experiment?
Right. So here there's not it's not changing topology of the electronic states. So there's a kind of Z2 topology in this for the band structure for this time reversal invariant topological insulator. So this experiment is allowing you to see flow K physics. So there's no topology change. It's just basically stacking states on top of one another. So even that effect is difficult. Of course, you raise the interesting question, which is, can you use light to change the topology of the system?
Like this
Yes, exactly.
I think that's on the next page.
Yeah, that's right. So you saw. Oops. Right. So the question is, can you change the topology? So this one is related to that paper. So this one is not starting with an insulator, closing the gap, and then opening it so that it's topological after the closing. So this one is you start with a gapless system, you open up a gap. So you basically go from a semimetal system into a gap system, which has a kind of topology associated with it. So this is graphene. In this case, you use circularly polarized light, which breaks the time reversal symmetry. So you have something which is kind of like a Chern insulator or a quantum anomalous Hall state, but in this pure time periodic regime. This experiment was a very difficult one to do, which is to measure transport, electrical transport in the presence of this light drive. So there's a lot of technical challenges associated with doing this, but the main takeaway from this is that the transport properties show something like a near quantization of the Hall conductance in the regime where you would expect it based on this flow K picture. So they're basically inducing like a topological band structure in this material, and it's reflected in topological light transport. So there's many reasons that it's not perfectly quantized. The light creates a lot of excitations in the system. It heats up the system. There's some subtleties in the bulk boundary correspondence in these flow K systems, which is not present in equilibrium. There's a much sharper bulk boundary correspondence in equilibrium, which is removed in this non-equilibrium situation. But anyway, it shows an interesting effect that you can get a kind of topological-like transport response from driving with light. Okay, so now I'm going to switch to some of the systems that that we looked at from the context of nonlinear phononics. So this first one, to connect with experiment chromium triiodide, it's a bilayer system. So there's an upper and a lower layer. Within the layers, there's a very strong ferromagnetic interaction between the local moments. And between the layers, there are weak van der Waals interactions. And so what we're going to try to do is influence that weaker interlayer magnetic interaction. So before I discuss doing that with light, I just want to show these three experiments which show that the energy scale associated with it is very weak. So at zero applied magnetic field, shown here is a cartoon of like the upper layer and the lower layer magnetizations from local moments. So they're oppositely oriented. The system has zero net moment. If you apply a magnetic field, you can easily polarize the two layers. So you overcome that interlayer exchange energy, change the sign of the field, it's polarized in the opposite direction. And the field here is not very large, on the order of 1 Tesla, which is well within what experiments can do in the laboratory routinely. If you apply a voltage to this bilayer system, you can also switch from this ground state antiferromagnetic property to the ferromagnetic regime. And you can apply pressure as well. So that's the third column over here. You apply pressure, and if the pressure is great enough, then you drive a transition into a ferromagnetic state. So together, these three experiments show that this energy scale associated with the interlayer magnetic exchange is not too large. And so we want to ask this question, can we create an analogous response with a laser drive? So you might ask first, why would we care to do that? If we can already do it 3 ways, why do we want to do it a 4th way? That's a good question. All of these are rather slow. So in order to, apply the field or to gate it or apply pressure, you can't do those things on a very rapid time scale. But if you can do it with light, then you have like femtosecond sort of time scale response. And moreover, it's generally reversible. So that's the motivation for doing it with light. And that was meant to be kind of a proof of principle to show that we could do something in a material which was possible via other means, but then use that as a stepping stone to do more complicated things. The sort of control that you would have over a lattice is significantly greater with light than you would have with strain or with external electric or magnetic fields or pressure. So this is the idea of nonlinear phononics, which is to use a high intensity light, which is tuned in frequency to match infrared active modes. So if you have a system with inversion symmetry, then the lattice vibrational modes are broken up into those of even and odd character. The infrared active modes are the ones that couple directly to the light. Raman modes couple at higher order processes at second order. And so the idea is to use these more light sensitive infrared modes, drive them to large amplitude. They're typically larger in frequency. And then when they're at large amplitude, you're no longer in the regime of decoupled phonons, because you're taking your potential between the atoms into a nonlinear regime. So you have coupling between even and odd modes. So the infrared modes at large amplitude actually activate the Raman modes. And because these IR modes are typically much higher in frequency, then you can think of a time average of those infrared modes acting on these Raman modes. So you average over the time of the period of these faster modes, and you get a position shift in the Raman mode's oscillation. So you change the equilibrium position in the crystal about which they're oscillating. So that's kind of what's shown here. So on this, the orange and the red is showing the higher frequency oscillations of this displacement vector Q sub IR, and the Raman mode Q sub R in the vertical direction, that's the blue. So it eventually oscillates down after the pulse of light passes through, but you have this transient shift from the dotted equilibrium position to a new equilibrium position. And while the system is oscillating about this new equilibrium position, you have a transient structural change in the crystal. So your symmetry change means you have a lot of possibilities for change in magnetic order. and electronic properties more broadly. So the idea then to study this in this particular material is to focus on the magnetic degrees of freedom and how they are affected by the lattice structural change. So the phonons are usually treated in a classical way. So you have some frequencies of these IR modes, some frequencies of the Raman modes, then they're nonlinear terms. This is a nonlinear term for the Raman mode. This is a coupling term between the square of the Raman mode and the linear term, square in the IR mode, linear term in the Raman mode, and that's going to lead to a shift in the equilibrium position. And then there are other terms here. These coefficients, like the frequencies, beta, gamma, delta, epsilon, all of those one takes from first principles calculations. So we had collaborators that helped us with those numbers. This sort of energy in the displacements is written down based on the symmetries of the crystal. And first principles gives us these sort of results. These are the frequencies of the Raman modes down here, the IR modes up here. And so you can see that there's a large separation of like an order of magnitude in the frequencies. Then one can look to see like how strongly are these various IR modes coupled to these and select out one which produces a dominant response. And on general grounds, the coupling of the Raman modes, the lower their frequencies, the greater the response will be to coupling to any of these, all things being equal. So the lowest frequency Raman modes are going to be the ones that predominantly respond. And so one can do a calculation based on first principles, which gives those coupling constants to see which particular Raman mode responds most. So this is the amplitude of the Raman mode time average as a function of the intensity of the light, which is driving the IR mode. The purple one shows the largest displacement. So we can focus on this particular mode and ask how it changes the interlayer magnetic exchange constants. There are many arrows here because it turns out that many different pairwise exchanges are important. So it's not just nearest neighbor, but it's second neighbor, third neighbor, etc. So we can look at the average effect of all of this, and that's shown here. So the black dotted curve is a 0, and this purple and the blue line indicates a sign change of an average exchange between these two layers, which is changing from a negative value to a positive value under a significantly large, substantially big displacement. So it's a sign change of the interlayer coupling from antiferromagnetic to ferromagnetic that occurs. Question?
I know there was some debate on the sign of the exchange coupling in the computations of these chromic triionide bilayers. Mm-hmm. And it seems to be very sensitive to the types of pseudopotentials and other parameters that we use.
Yeah.
So how reliable is this sign change?
Well, I would say that it's as accurate as those calculations, first principles calculations. So we certainly know that it's not unexpected. That's why I gave the experimental overview in the beginning. So experimentally, it's antiferromagnetic for bilayer because the experiments are unambiguous on that. And it can be changed with an applied field gating pressure. So if we have a density functional theory calculation which gives us antiferromagnetic order, then it agrees with the experiment. So our starting point is good. And the order of magnitude for the basic value of this is consistent with those experiments that I showed. So based on those 2 points, I would say that it's not unreasonable. But it's true that we then used the lattice displacements from this, and then first principles was used to calculate what would the new exchange constants be. So ultimately, it needs to be tested against the experiment. But it should be a fairly straightforward experiment to do because you have a system which goes from 0 moment to finite moment. And so there's a lot of big probes you could do, like Kerr rotation or Faraday rotation or something like that, which are going to be sensitive to the dramatic change from 0 moment to finite moment. So as far as I know, this hasn't been published experimentally. I don't know if it's been tried or not, but no one had said, oh, I did that experiment and I found that it does do that. But it should be straightforward to do. And it's in the ballpark. I would say that the main caveat here is not related to the sign of the exchange, but the time scales involved. Because the pulse of light that you're applying to the system has a time scale associated with it, which is of order the interlayer magnetic exchange constant inverse itself. So I think that the more dangerous question is whether there's enough time for the magnetic order to reorient when the structural change is there. Because you have to have things reorient, but it's going to be on the scale of the inverse interlayer exchange. So I would say that that's, to me, the bigger worry than whether or not the numbers are right, whether the system can respond quickly enough and change its magnetic order in response to the change in the preferred order from the exchange.
A quick technical question. To calculate the GIJ, proposing a spin model and then doing different energy setups to fit this model.
Right. So this Hamiltonian is fairly well established from various sorts of experiments. So basically, we just wanted to find, the exchange. So this is within the layer, and then between the layer, this Heisenberg form is believed to be a pretty good approximation. So basically, we just wanted to compute these JIJs. So those were computed from first principles for like a frozen phonon approximation, it's called. So you freeze the lattice, you compute these, you apply the light, which distorts the lattice in a particular way. It turns out it's a shear mode. So there's a shear. So that shear is frozen in. Then you recompute these J's, and you do that for different amounts of shear, essentially. So that's what generates this curve right here. And so the J that appears here is basically, it's this effective J, so it's averaging over all of these, so that there's one number that can be produced versus all of this. So the gray ones are various J's, and the colored ones, the blue and the blue dashed and the purple, are averaged.
Okay, just because there are, you can calculate using these Lichtenstein equations with a Green's function or total energy calculations. I'm guessing that you guys use the total energy DFT calculations to get to this GIJ, or?
Yes. Okay. Yeah. But we did use that Green's function method that you mentioned on the next material that we looked at, which is this one, because it allows us to handle some disorder effects, which we did not treat there. So this material is very similar to the one that I just mentioned, the chromium triiodide. This is manganese bismuth 2 tellurium 4, or replacing antimony with the bismuth with antimony. Very similar analysis that we did, and this material, though, is known to have a lot of defects in it, so we were interested in the effects of the defects and how they would change the effective interaction. So we put in anti-site defects. That's the ASD, which is thought to be the most common one there. And the upshot is that the picture doesn't change. But we used this, I think, the same Green's function method you mentioned there to treat some of the disorder effects here. In addition to getting the interlayer magnetic exchange, and in the chromium triiodide, it was a shear mode. For this particular system, it's a breathing mode. So the distance between the two layers is changed. That's the one which activates the exchange sign change between the layers. So it's interesting that these two materials have a difference in their microscopic details, but the same physical effect of the interlayer magnetic exchange changing its sign. An additional feature that we find here is that the band topology changes. So there's a Chern number change in the band topology when the system goes from the anti-ferromagnetic bilayer with zero net moment to the ferromagnetic bilayer with a finite moment. There's a topological transition, which you can see from a band inversion. So this one has, in addition to its magnetic transition, also a topological band transition. So this is an example where you can change band topology via this nonlinear phononics route. Okay, so now I want to switch gears. So up till now, I was discussing the direct coupling of light to the phonons. Now I want to switch to the direct coupling of light to the electrons. And I want to focus on nonlinear optical responses in Weyl systems. So these are of interest, particularly the nonlinear part, because it's thought to be a probe of quantum geometry. So, this is the sort of object that now the attention has been drawn to within those in my community in condensed matter physics. So this second part here, this Berry curvature, is what underlies most of what is understood about topological band properties. Chern numbers and other sort of invariants for topological crystalline insulators. You have mirror turn numbers, etc. The Berry curvature usually is playing the starring role, but it was realized that this is just half, if you will, of a more general like quantum geometric tensor, and it's the imaginary part of this object. So the question has become, what is the interesting role played by this quantum metric, the real part, so the other half of this tensor? So there's been a lot of work done in superconducting systems, in particular, that I won't talk about, that shows that there's some bounds that one can play on two-dimensional superfluid stiffness, etc. There's very interesting questions that are related to twisted bilayer graphene around the magic angle, where the bands are very flat. You have no kinetic energy of the electrons, yet they still pair to form a superfluid state. And many of those interesting questions can be understood in terms of the role that the quantum metric is playing. But besides that best understood example of two-dimensional flat band superconductivity, there's still a lot of open questions about what are the signatures of this object in various types of measurements. And so the Weyl systems provide an example of a quantized response in a higher order response quantity. So quantum Hall effect, quantized Hall conductivity is a linear response quantization. It turns out that there's a quantization in the second order response from Weyl systems, and it also involves not just the Berry curvature, but the quantum metric. So that's kind of the reason that attention is drawn to Weyl systems and also nonlinear optical responses. So this is kind of the tip of an iceberg of looking at the ways that material responses to light can reveal information about this quantum metric. And I mentioned it at the beginning, I'll mention it again, that this is expressed in terms of the block states. So this is all single particle physics, this tensor, and a nearly untapped question is how to generalize anything that is understood about this more general object to a truly interacting many-body system, where you have much more complicated wave functions than just these block states. So very little has been done there. Okay, so I'm going to look then at Weyl systems. And if we look at the second order response, so there's a photocurrent. So you can think of a second order response coming from some two powers of the electric field. So I could think of one electric field at frequency omega, another at frequency minus omega. So the sum of the two is zero frequency, and that induces like a DC photocurrent. So there's a current which is induced in a material in the second order response to the electric field. And there's components called a shift current and an injection current. And these contain elements of this quantum geometric tensor. And so in that way, this photocurrent response is very interesting. So we've already seen a number of talks that talked about Weyl systems, so I'll go kind of quickly over this. I just want to emphasize that there's different classifications of the Weyl. So there's so-called type 1 and type 2. The type 1 are the ones that mainly we hear about, but you can have a tilt to this linear dispersion that is so significant that you tilt the cone down through an energy surface, and at that point it now becomes a type 2 Weyl system, and they can have different responses. I also want to remind everyone that there are these topological charges or chiral charges associated with Weyl points that must come in pairs. So one acts as a sink, another as a source of Berry curvature, and there are these Fermi arcs on the surface. And the Weyl materials require either broken time reversal or inversion, or both of them. So that's going to be important for the response. There's some very nice papers here, which were important in establishing some of the early results in the field. So Weyl node stability, I think we've heard about this earlier. I don't want to say too much about it, but they typically are very stable. There's this chiral charge associated with it, and the work that I'm going to talk about, we're going to look at the differences between 1, 2, and 3 values of this chiral charge. So in units of 1, we can have different integer amounts. So we could have like a Weyl point charge 1, that's a typical one, 2, 3, or up to 4 are allowed in a stable configuration in the lattice. Let's see, so how much time do I have?
20 minutes.
20 minutes, okay. So the identification of the Weyl materials is very similar to the topological insulators. It's done by photoemission, so people look for these Fermi arcs. Weyl points in the bulk, you look for Fermi arcs. This is theory, this is experiment. And typically you have a reasonable level of agreement between the experimental photoemission and theoretical calculations. Not quite at the level of topological insulators, but still you can see that the main features are there. So the response of Weyl systems to light, one can look at photocurrents. You get a very significant response depending on whether you have linearly polarized or left circularly polarized or right circularly polarized light. That's one of the parameters that one would like to change. And the interesting thing, perhaps, for this community is a quantized response. So in order to get a quantized response, a photogalvanic response, it's a quantized current response from a Weyl system, you need to isolate a Weyl node. So basically, you need to create an energy imbalance, so push one below the Fermi level, so that for low frequency light, transitions are poly-blocked. You can't create any excitations because there's not an empty state to excite the electron into. And you can do this by a combination of mirror and inversion symmetry breaking. If you can isolate a single Weyl node in this situation, then only one of these Weyl nodes is available. It's not poly-blocked. And then you can look at this quantity here. So how is the current that's induced for right circularly polarized versus left circularly polarized related to one another? So you take the difference of them. There's some fundamental constants. I is the intensity of the light, and then C is the charge of the Weyl point. So basically, this quantity gives you direct access. It's a quantized second order response once you divide through by quantities related to the intensity of the light. And this is the sort of thing that one expects in this situation. So this is what the experiment looks like. So you don't have something which is perfectly quantized, but it certainly looks like it's headed there. And there are a lot of reasons that this may not be well quantized. It could be transitions to higher bands. It could be interaction effects. But nevertheless, it's an important example of a quantization effect in a higher order correlation function. And it reveals information about this quantum geometry, which is the reason that people are interested in it. Okay, so now I'm going to switch. Yeah.
Is there a counterpart in 2D? Quantized representation.
No, I'm not aware of a 2D example, but there are like two-dimensional transport experiments which have revealed some other aspects of the quantum metric. So the quantum metric dipole can be revealed in some transport measurements in 2D. But I'm not aware of like a quantized response of this sort in 2D. Yeah, question?
Is a ferromagnetic material or is it ferromagnetic light?
This, oh, sorry, this one? Yeah, this one is not a magnetic material.
That would be relevant or irrelevant?
So it does make a difference, you know, but yeah, the details are different. Okay, so let me show you a little bit about the what's under the hood in these sort of calculations. So to compute the nonlinear response, so you can see how the quantum geometry enters. So we're interested in a kind of DC response. So we have this second order conductivity tensor, electric field components. So A, B, and C are X, Y, and Z directions. So this is a DC current in the A direction coming from electric fields in the B and C directions at opposite frequencies to give us a total frequency response omega. And typically we're interested in the DC current so that this is going to zero. It has two main components, this shift current and the injection current. Each of these are expressed in terms of little r's. The little r's are expressed in terms of basically pieces of Berry connection. So you have like block states. This is like U sub m or U sub n. So you're taking basically the same sort of quantities that enter into the Berry connection, which enter into the Berry curvature, and also correspondingly the quantum metric. So they're folded in general in a somewhat complicated way, and you end up with a convolution over these various pieces to compute these injection shift currents. And this is what you get in the second order response. It turns out that, as you go to higher order responses, which are covered in both of these articles here, this particular one is very nice, you get richer and richer geometric structure from the wave functions that is appearing in the responses. So we looked at these cases of Weyl nodes, one single isolated Weyl node for charge 1, 2, 3, and 4. This effective low energy Hamiltonian covers all of those cases. The joint density of states has a kind of universal frequency dependence, which has an exponent that depends on the charge of the Weyl nodes. We can compute all components of this shift conductivity or injection conductivity tensor, and then we can show that if you sum over all the different components of the injection, then for all of these values of n, not just for n equals to 1 or 2, but all the way up to 4, you get this quantized response. So the total response is proportional to the chiral charge of the node. So one thing that is very important for the experimental observation is how well does the low energy model do compared to realistic band structure? Because there are other bands around. There's also curvature, and how much does this curvature of the bands around from that linearly dispersing Weyl regime play a role? So we did a comparison of a charge 2 low energy model, which includes some curvature corrections. That's the green curve. And compared it directly with the tight binding model, which doesn't make any assumptions on the low energy theory, just computes it directly. So basically, you can compare the yellow with the blue and see that in general, there's some differences as a function of frequency. But you can, with just small corrections, you basically get the green to agree with the yellow. So if you just look at the leading order corrections to the linear dispersion, then generally you get a highly accurate result in terms of the second order response, which is a somewhat surprising result, at least we thought, that small corrections make a very big effect in terms of agreement with experiment. So that's kind of one lesson for connecting to experiment. We can compare a 4-band theory to a 2-band theory that includes even more bands, which transitions could occur to. And here there's significant effects in general. So the curve to look at is this one right here. It's a little bit difficult to see, but this dotted curve is what one would get for the 2-band low energy theory. The other curves, there's a parameter here, delta, which is saying like how big the gap is between this low energy model and the full 4-band model. And generally, as the gap increases, it's moving up this way, then the quantization gets better and better. So this is maybe one way to connect with the experiment, that higher order bands can really disrupt this quantization. So this is not nearly as appealing as the quantum Hall systems, where whatever other bands that are around, you still get very high levels of quantization. The Weyl 4 system, that's new. Basically, we kind of delineated, where you expect a strong quantization there. Somewhat specialized. I don't want to spend a lot of time there. Save time for the last topics. So, in summary, what we've done here is we've looked at the nonlinear optical response of these Weyl systems, shown how the shifted injection currents are related to properties of the Weyl system, such as their topological charge, tilt, and chemical potential. So, the various tables that I show you basically allow you a way to do optical experiments and measure the Weyl properties independent of photo emission. So if some reason your system doesn't have good surface preparation properties or something like that, you can measure the Weyl system by looking at the second order response through different polarizations of light, frequencies, and angles of incidence with the material. Kind of a final topic related to this nonlinear optical response is the way that you can use it to detect the phase of a system, such as the superconductor. So there's this interesting compound, 4-HB tantalum disulfide, which is a candidate topological superconductor. If you look at STM experiments, so this is like a step edge between like one layer of this material dropping down to another layer. They have 1T and 1H symmetries for the experts. And if you look at the boundary here in scanning tunneling microscopy, you see what looks like a metallic edge mode, which is running around. It's decaying exponentially. And so the question is this edge mode a topological edge mode or not? So it's desirable to have some additional experiments that one can do besides just this scanning tunneling microscope experiments that would provide complementary evidence for whether the state is topological or not. And with the background of the quantum geometry and the nonlinear optical response, then you can imagine that it might be interesting to look at the nonlinear optical response of the superconductor and ask whether you can detect its superconducting phase within the second order response. And indeed, the answer is yes. So there's a model which is written here. It has a phase diagram that looks something like this. There are, it's a multi-orbital model. There's pairing between different orbitals on a given site. These are d orbitals, and some of them have even parity and odd parity. So it's basically a mix of like an S and a P wave superconductor because it has broken inversion symmetry, and as a function of the ratio of the pairing, the even and odd parity pairing, that's this ratio C, then you can change from a trivial superconductor to a nodal superconductor to a time reversal invariant topological superconductor. That's the TRITOPS. So all of these are time reversal preserving. You tune them by tuning the ratio of the admixture of even and odd parity superconductivity. And there's another axis alpha, which is a Rashba type spin orbit coupling, which is present. So each of these phases has a distinct frequency dependence of the second order response. So if you're an experimentalist, you can look for this frequency dependence and then relate it to these phases, provided that you at least have a starting point for what the candidate phases are in the system. Then you can indeed see that sort of information. This is just kind of more details about it, but the basic result is here. Okay, so in the final few minutes, the final topic that I want to discuss is chiral phonons. So that's what I mentioned. So chiral phonons carry angular momentum, and therefore systems that we're familiar with, such as spins, any phenomena that we have for spin systems in principle is possible for chiral phonons. So you could have a phonon-Zeeman effect. You could have two degenerate, like right and left, moving phonons. You apply a magnetic field, you're going to split those with the Zeeman effect. And it's a very interesting question. How does the splitting depend on the strength of the magnetic field? That's going to measure essentially the G factor of these chiral phonons. And there's some interesting things to say on that point. And as I mentioned, you can transfer light angular momentum to it from the lattice of chiral phonons. They can be at different points in the Baron zone. So you could have phonons which are zone-centered or zone-boundary, and the responses are rather different. There's a very natural connection to topological electronic band structures with the strong momentum locking. And there's this transfer between spins and lattices. So the field has become very active in recent years. So I've put a few papers here. There's a spin Seebeck effect that's related to angular momentum, which is moved via chiral phonons. The standard spin Seebeck effects are typically coming from electron spins. There's various reports of observations in different materials. This is the issue that you raised, Emil, about like the truly chiral phonons versus just the ones with finite angular momentum. People are using like X-ray scattering to observe them. You can see that there's a wide variety of different materials. There's tungsten diselenide, mercury sulfide, quartz, and there's others. So what I want to focus on is the Zeeman phonon effect. So how does the energy of the chiral phonon split in a magnetic field? So basically it's a Zeeman sort of coupling term here. There's a magnetic field. This is the angular momentum of the ion. If you look at this gyromagnetic ratio, it goes as 1 over the mass of the ion. So if you were to compare this to electrons, then you would expect it to be on the order of 2,000 times smaller, because a typical ion mass is about 2,000 times bigger than an electron mass. So if you find an experiment which shows that it splits on the same scale as the electron, then it's an interesting observation, and it's calling for an explanation. So that's in fact what happened. So some collaborators of mine were looking at this lead telluride material, a thermoelectric material, and they found exactly that. That if they looked at the splitting in a magnetic field of these chiral phonons, and they found a G factor which was on the order of the electron, or approaching that. And the question is, what's going on there? They added in tin to make it a topological crystalline insulator. So now there's an interplay between band topology and chiral phonons. And again, they get an interesting effect. So as you go from the trivial phase as a function of this tin concentration X into the topological phase, then you get a huge jump in this G factor. And these basically can be understood as effects where the electron topology is getting imprinted into the phonons. And you can model this with a sort of band theory. And the final example that I'll give, because I'm running out of time, is this very different material class, cobalt titanate. So very different than all of the chiral phonon materials that I mentioned before. This one, in addition, has Dirac-like features in its magnon structure. So it's kind of a simple version of topology, if you will, having this kind of Dirac-like feature in the magnons. So in addition to the chiral phonons, it also has Dirac-like magnon features. And we can look at then the chiral phonons in this with a very different model. So we could explain the effect in lead tin telluride from a band point of view in order to explain the large G factor in this material, which is strongly correlated in insulating and magnetic. We needed to look at the local orbital structure. So basically, there are local atomic transitions which are resonant with certain phonon modes. And at the end of the day, to cut my talk right to the end, we can do an analysis looking at all the coupling between those modes, and we come up with splitting in the magnetic field, which is in fairly good quantitative agreement with the experiments. Okay, so chiral phonons, a brief summary here, very interesting topic. Angular momentum control in like a new degree of freedom. Pretty much anything you can do with spins, you can do with these phonons now. And it's kind of open to understand in detail what are the mechanisms that are responsible for those large G factors, but there are many other questions as well. And finally, I'll thank my collaborators in all these projects. And thank you for your attention.